Hello and welcome back to another episode of the A-Level Cookbook. Today we're going to be doing the Edexcel A-Level Chemistry Paper 1 from June 2022. So this question's about atomic structure in the periodic table. Complete the table to show the relative charges and masses for a neutron and an electron. So a neutron has 0 as its relative charge, an electron is -1. The relative mass of a neutron is 1, and then the relative mass of an electron is 1 over 1840. Although it does allow a range of values from 1 over 1,800 to 1 over 1,200. But it says you should not put 0 here, so you can't really do that because it doesn't have 0 mass. So electromagnetic radiation and all that stuff, and the wavelengths and things can range from infrared, which is quite long wavelength, to ultraviolet. Now, when you have a decreasing wavelength, you have an increasing frequency. So this can provide evidence of quantum shells, because an electron can be excited to a higher energy state, like a higher energy, by absorbing a set amount of energy from a wave. Depending on the wavelength and the frequency of it. So if you give them the right wavelength of ultraviolet, it will absorb it. It'll get excited, and then to go back down, it will re-emit it back out. If it re-emits that, then we can see that on an emission spectrum. So for example, if you put white light is every single color, and then if you absorb it and it re-emits it, and let's say it puts out green light, you'll see a strip here, a line on the emission spectrum of green on a background of just black, because black means no light, white is all the light possible. And these colored lines can tell us that you need a specific wavelength for the electron to have been excited and send it back out, meaning that you can't just dash all the energy you want to it. It has to be the right amount and specifics. So that means they're fixed values to go from here to here, which gives us those quantum shells. So it says draw the shape of a p orbital is this. Cool. The melting temperatures of two elements of the period are given in this table. We've got silicon and chlorine. Explain in terms of the structure and bonding of each one. Explain these values. This should be 3 marks. And for those that are getting this wrong because they're saying the wrong things, really need to stop doing it. What you do is you say what you see first, and then you describe it. So silicon has the higher melting point. Chlorine has, Cl2, remember, has the lower melting point. If it has a higher melting point, it means that there's more energy required to break. And then we need to think what bonds are in silicon. So it's a giant covalent structure, or macromolecular. So it means you need more energy required to break the covalent bonds, because it is macromolecular. Cl2 has lower melting points because you need less energy required to break, and you need to decide what bonds are being broken in this. So it's a simple molecule, so it's going to be there's less energy required to break. People call them London forces, you could call them van der Waals forces, but you got less energy required to break these, therefore it's a lower melting point. There you go. And now because it is a simple molecule. That's it. You do each one by one, and you'll never forget what to say and never get the wrong marks, and that gets everything. A mistake I see people say is that they're breaking the covalent bonds in chlorine. Cl2 is this. If it's Cl2, for example, liquid, it's still this. If it's a gas, it's still this, because this covalent bond is untouched. You're not breaking the covalent bond. Otherwise, you would just have Cl atoms, and that is incorrect. When you're boiling this, you're breaking these van der Waals forces or London forces between the two molecules. It's called intermolecular forces. Inter means between molecules. In giant covalent, you've got one thing bonded to the next, 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 blah, 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 blah. So you are breaking the covalent bonds here, because everything is bonded to each other with covalent bonds. So this question's about elements in the group 2 of the periodic table. Magnesium powder is added to a beaker of water containing a few drops of universal indicator. The apparatus is set up, and then it's allowed to stand for a few days. So we've got magnesium powder, we've got filter funnel, we've got water and universal indicator, and they've got a test tube filled with water. So then what's happening here? Well, let's see. What changes will be happening after 2 days? So filter funnel, magnesium powder, what's happening is that the water in this test tube is reacting with the magnesium powder, and it's going to react slowly. It's going to do its job. So then what happens is that you first of all are going to get the water level is going to drop in this tube, and gas is going to collect, because group 2 methyl plus water makes methyl hydroxide and hydrogen gas. So then it means you're going to make, well, first of all, it's again changes that you will see. So it's not asking about what's happening chemically, it's what you're seeing. So water level in tube drops, or you could say the gas collects the tube, and then the universal indicators here, this is going to form magnesium, it's going to form magnesium hydroxide, which can move through this filter funnel into here, and that's alkaline. So it's going to go from green, so the universal indicator, that is, goes from green Whoops, green to purple. It's been left for a few days, so it's had enough time to start doing its job. Explain how the trend and the reactivity of group 2 elements is determined by the electron configuration. So in this question, you don't need to be yapping about all kinds of other random stuff. So what people do, and this is what the examiner report says, they'll describe everything else, but then just do not explain why reactivity increases, which is really weird. I don't know why you're going through all that effort to say all of this stuff and then not concluding. So all the time, say it step by step. Down group 2, the only thing that is changing is that you have more shells. So if you have more shells, so step by step is, you've got an increasing number of shells, which means there is more shielding of the outermost electron. Well, the outermost electrons, sorry, I should say. Therefore, the attraction between these electrons and the nucleus decreases, so the attraction between the electrons and the nucleus has decreased. So then, it means the electron is lost more easily. So then your reactivity increases. Because if you're losing the electron more easily, that means your first ionization energy decreases. That's why when you're losing electrons, you're doing ionization. So first or second and so forth. So it means it's, being lost more easily. But a lot of people just kind of said this, and then this, and maybe this, and that was it. And I was like, well, how does that link to the reactivity part? Do what the question's telling you. Trend, reactivity, something to do with electron configurations. Go for it. Next. So calcium reacts with chlorine. Explain in terms of electrons why this is a redox reaction. So you can't just jump in and say, oh, oxidation number, this and that, blah, blah, blah. It's any question that's talking about oxidation and reduction, you have to talk about the movement of electrons, the gain or loss of them. Calcium is going from 0, and then its oxidation number becomes +2, and then chlorine is from 0 to -1, but there's 2 lots of that. So it's, again, any redox reaction, even if it doesn't say it in terms of electrons, just do it. So that means that Ca2 plus oxidation number is from 0 to +2, so it's oxidized. So it's lost 2 electrons. Cl2, oxidation number goes from 0 to -1 each. So it's been reduced. And each has gained 1 electron. You'll never, ever, ever lose marks if you do it this way. So do it that way, please. An experiment was carried out to determine the molar volume of hydrogen at room temperature. This much magnesium was added to excess hydrochloric acid and this much hydrogen was produced. Calculate the molar volume of hydrogen from the results of this experiment and then included results in your answer. So here, people just jumped into working out moles and then just didn't know what to do with it. Use your common sense and think for a sec. You're adding magnesium to excess hydrochloric acid. And here, that's the magnesium, there's extra of this. And it's asking you, calculate the molar volume of the hydrogen from the results of this experiment. They've told you that this is how much hydrogen that was produced. All of the hydrogen must have come from these two reacting. The reason they did excess of this is to make sure all of that's reacted. So if all of this is reacted, then all of this will eventually have come from the reaction between this and this. So the moles of this is going to be the moles of that regardless. So then, what we do is you work out your moles of magnesium, which is going to be 0.035 grams over its MR, which is what, 24.3? Which gives you 1.4403 times 10 to the -3 moles. The molar volume is the volume per mole of something, right? So they've told you that it's 32 centimeters cubed. So if it's 32 centimeters cubed that they have produced, its molar volume, the volume of it released per mole, is 1.4403 times 10 to the -3, which is 32 over 1.4403 times 10 to the -3, which gives you, and that gives you 22217.6 centimeters cubed per mole, but we want to give it to the same number of significant figures in the question, and also we want to put it in standard form ideally. So if we do that, that is 2.22 times 10 to the 4 centimeters cubed moles minus 1. We'll go with 2 significant figures because that's what the question's given us. There you go. So this question is about the elements in group 7 and some of their compounds. What is the color of iodine in the solid and gas state? So it is gray-black as a solid and it's purple as a gas. It's D. Which of these reactions occurs? You can see that these are all halogens reacting with something halide. So we're looking at our displacement reaction. So generally speaking, this is the order that we see. This will displace this, this will displace this, this will displace this. You can't go back up. So any one of these where you're seeing bromines becoming bromide and swapping, then you're fine. So the only one that does that is that, well, bromine can't become bromide and displace the Cl. It can't do that, so A's out. B can't do that. C can do that, so it's C. D can't do that. So the halogens can form halide ions or in reactions complete the electronic configuration of the chloride ion. So one quick shortcut you can use is that this is the S block, remember? That's your D. It's your P block. Now this is period 1, period 2, period 3, period 4, period 5, period 6. So chlorine is here, so it's in period 3 and it's P1, 2, 3, 4, 5. So its outermost electron normally is going to be in 3p, 5. Right? And that trick works for literally everything. So Ca would be, so it's S2 and it's in period 4. So before S2. The D block is just where it gets a bit weird, because although they're in period 4, remember that the 4s orbital fills first, so these are all actually 3D instead. So 3D1, 3D2, 3D3, and so forth. So just be cautious about that, but you can use that to work out this question quite quickly, because I know that the normal chlorine atom that's happy has 3p5 in its outer, but it's a chloride ion, so it will have gained an extra electron, so I know it's going to end in 3p6. The rest is just filling in the rest out. So 1s2, 2s2, 2p6, 3s2, and 3p6 done. So the standard electrode potentials for two half-cell equations including bromine are given, and then here we are, and it says explain why the disproportionation of bromine is not thermodynamically feasible under standard conditions, and include the overall equation for the disproportionation and its E-cell value. So people are going to dive in and be like, oh my god, this one's more negative, this one's more positive, therefore oxidation reduction, right? That's not what it's asking. Sometimes in the question it will tell you which way you have to take this, right? It might say it's discharging or recharging, whatever. Here it's told you this is the disproportionation of bromine. So it can't be you've got to just do one or the other. It's this bromine has to be both oxidized and reduced. So we need to have an equation where bromine is reduced and one where it is oxidized. So in the first one, bromine is being reduced. So the first equation is going to be 2A minus goes to 2Br minus aqueous. We don't then say, oh, the other one, because it's more positive, it needs to be whatever, right? Like, it's not, because they've told you which direction you need to go in. And it is bromine. So this equation means that we have to do the oxidation direction of it, which means it's going to be Br2 plus 2H2O liquid becomes 2HOBr aqueous plus 2H plus aqueous plus 2E minus, as in, it's forcing it in this direction. Okay? So that means that this is being reduced. This one is being oxidized. So then, we're combining them together, we would end up with Br2. So that's what? Br2 and Br2. So that's 2Br2 plus 2H2O. Liquid goes to 2HOB aqueous plus 2Br minus aqueous plus 2H plus. Tidy this up to get Br2 aqueous plus H2O. Liquid becomes, HOBr aqueous plus, and then these two are going to combine to give you HBr aqueous, although it does allow keeping these here as well. So then, that's the overall equation. We need to describe why it's not feasible. E cell equals whatever's being E reduced minus E oxidized. Now what that means is we need to look at what's being reduced and what's oxidized. So this one's being reduced, so it's 1.09 volts, minus what's being oxidized, which is 1.57. If we do that, we end up getting minus 0.48. The E cell is less than 0, therefore it's not feasible. There you go. So it's really important not to dive into a routine and think, oh my god, it must be oxidized or reduced, blah, blah, blah. Look at the question, and then it will tell you whether it's oxidized or reduced instead. Here, it's told you that we're disproportionating bromine, so we need to make sure our equations have Br2 being oxidized and being reduced and then combined. So disproportionation of bromine happens in water to a small extent at 298 Kelvin. Give a possible reason as to why. Well, if we look at this overall equation here, this is an equilibrium, right? So although, there's very small amounts of it going this way, there's still going to be a little bit happening. So you could say that. So disproportionation is an equilibrium reaction here. So there's still a small amount, even if the product's, concentration is low. Because for an equilibrium to happen, it has to be going this way, and then eventually level out and whatever, right? So there's still got to be at least some of that happening. Also, you could say, for example, with all of these, we're assuming that this is perfectly measured so that your solutions and concentrations are all 1 mole per decimeter cubed. It might not be the case. Or it could be, we've done stuff to shift the equilibrium, so we might put too much water in, moving it this way. Or, this could further undergo disproportionation itself. So there's a lot of reasons why. It's talking about possible problems with the assumptions we made in this question. The hydrogen halides have the general formula HX, where X is the symbol of the hydrogen, which diagram shows the trend in the boiling temperatures between the hydrogen halides. So the difference between all of them, what's the thing that's going to be doing the boiling is whenever you're thinking about boiling or melting temperatures, you need to think, what bonds am I breaking? Across the board, you're going to be breaking permanent dipole and London forces, or van der Waals forces, whatever you want to call them, between these, right? But we have HF here. H bonded to NORF means hydrogen bonds. So you're going to have this really high one for HF. It's going to drop and then it's going to climb back up, because in between all of these ones, your van der Waals forces, your London's forces, whatever you call them, I'm going to call them London forces for now on, increase. So that means the only one that explains that is C. Now, what type of reaction happens when ammonia gas reacts with hydrogen chloride gas, so HCl plus NH3? The only thing that you can possibly make, well, you should be able to recognize, is that you're going to make NH4Cl. So the NH3 has become NH4, so it's gained an H+. The HCl has become the Cl-, it has lost an H+. If it's lost an H+, it's acting as an acid. If it's gained as an H+, it's a base. No matter what it is in the universe. So it's an acid-base reaction. There you go. So this question is about structure and bonding. Ionic bonding is the strong electrostatic attraction between two oppositely charged ions, which is anions and cations. There you go. An aqueous solution of copper-2 chlorate was electrolyzed using this apparatus in this diagram. So E and F, here is 6 volts, whatever. Here's your copper chromate solution. Deduce the colors of the solutions in regions E and F after electrolysis has occurred. So we're dealing with copper chromate, which means we're going to have a Cu2 plus and we're going to have a CrO42 minus. This Cu2 plus is going to go to the negative electrode, and this CrO42 minus is going to go to the positive electrode. So that means that in the E, we've got our CrO42 minus, which is yellow, and then we've got our F, which is the Cu2 plus, which is blue. So it's just, unfortunately, just having to remember those colors. So some ionic radii are given in this table. Deduce the formula of the compound form of the ions that has the strongest ionic bonding. So we want, remember, the ionic bonding is the electrostatic attraction between two oppositely charged ions. If I have something with loads and loads and loads and loads and loads and loads and loads of shells, is this electron attracted to the nucleus or something else? So that's, like the other one's got loads of shells. It's not a very strong ionic bond. Whereas if we've got something with like very little, and it's here and here, that's like strong. So we want the smallest things here bonded with each other. So between Na and Mg2 plus, it's going to be Mg2 plus, and then because between Cl minus and Br minus, it's going to be the Cl minus. So it's going to be MgCl2. The names of 4 substances are given, so here we go, and then it says which of these exist at room temperature as a giant lattice of oppositely charged ions. So a giant lattice of oppositely charged ions is describing ionic bonding. So whichever one of these has ions. So that's metallic bonding, nope. That's a simple molecule, nope. This is giant covalence, nope. So it has to be S, which is D, which is really confusing because they put S and D, like, you know what I mean? Like, just why don't you just call it ADC, whatever, right? So the question tells you, what you need to look for. So which of these substances has a high melting temperature and conducts electricity when solid and when molten? So the only one that can must be copper, because that's, it's a metal. Metals generally can when they're a solid because they have those electrons that delocalize and able to move. Silica, so iodine is a simple molecule. It doesn't have any delocalized electrons. Silicon doesn't, because it doesn't have any delocalized electrons. So these can only conduct electricity when it's molten or the ions are free or in solution. So because they can only carry charge when able to move. In solid, they're fixed in place. So you can't do that. So water has 2 significant anomalous properties. It has a higher melting temperature than hydrogen sulfide, even though it has fewer electrons. The density of ice at 0 is less than that of water at 0. Explain these properties. You should use a label diagram to show the intermolecular forces between 2 molecules of water. So let's do this one by one. If we're going to start yapping about like how, hydrogen bonds give all of its properties, it's probably best to start with describing what a hydrogen bond is. So a hydrogen bond is when hydrogen is bonded to oxygen, remember? And you've got your delta negative, delta positive dipoles here. Then you've got another hydrogen bond, chilling air. And you've got a hydrogen bond between the hydrogen of the delta positive hydrogen here and the oxygen of the other thing. Now, the thing that's interesting about hydrogen bonds in water, because ammonia doesn't do this as well either, is that this angle here is 180 degrees. And it's not talking about the bond around the oxygen, it's talking about the hydrogen bond itself. So when we're looking at the melting point between these two, we are comparing hydrogen bonds versus what's being broken between these, which is predominantly van der Waals forces, London forces, or permanent dipole dipoles. So hydrogen bonding is stronger than the van der Waals or London forces, whatever you call them, in H2S, meaning more energy needed to break them. Therefore, it's got a higher melting point. So there's that one dealt with. And then that's that. So also it says even though it has fewer electrons in the molecules, this outweighs the effect of having less electrons because the hydrogen bonds are that strong. And then, oh, whoops, there's space down there, whoops. And then it says the density of ice is less than that of water. So when you have ice, what happens is these water molecules arrange themselves in such a way so that you have lots and lots of space between them. Like, you know, kind of like this almost. Whoops, yeah, like this. So then what happens is, because it's doing that, these hydrogen bonds make them spread out more, and you've got this like latticey look going on here. And then what happens is these atoms are spreading out more and more and more, but when you break them, they break down, and then you get those hydrogen molecules all again sort of like dispersing between each other. And because they're more spread out, it means the ice is less dense. So we need to talk about that into words now. So what happens is that as ice, that's supposed to be a hexagon, I've drawn that terribly, but H2O is arranged, well, the molecules, sorry, are arranged as a lattice, or you could say a hexagon. And as water, and that, sorry, makes it less dense. As water, the water molecules are closer. So you've got more density because there's more particles. So there's more H2Os in a given volume. That's exactly why water floats on water. Sorry, water floats on ice. So this question is about enthalpy changes and energy changes. Magnesium carbonate reacts with dilute hydrochloric acid at room temperature. Here we go. When the reaction is carried out in a sealed container with a constant volume, the heat energy change is not the same as the enthalpy change for this reaction. Give a reason why. So in this case, so every single enthalpy change in the universe is measured in standard conditions where you keep the pressure and the temperature consistent, because those two things screw up the enthalpy change. This question has told you that we've done it in a sealed container with a constant volume, but they've said that the enthalpy change, heat energy change, is not the same as the enthalpy change this reaction should be. Now, a lot of people are tempted to jump straight to saying, oh, maybe heat's lost and this and that, blah, blah, blah. Enthalpy is dependent on temperature and pressure. The heat's going to increase, and we're assuming it's probably, there's nothing here to suggest, like, for example, where the heat energy is going to and stuff. We don't know anything about how the heat was measured. All we know is stuff to do with the volume and the pressure. If we see here, we're going from a solid to plus aqueous to a gas being produced. If we do that, if there's gas in here and it's in a fixed volume, it's going to increase the pressure. So CO2 gas is produced. This increases the pressure. So therefore the pressure isn't constant, and that's what makes it different. So just be careful to look at what the question's given you here rather than yapping about what you think it could be, because it literally says in the mark scheme to ignore references to temperature. So then it says, state what is meant by the standard enthalpy of formation of aluminium oxide, and then include standard conditions. So it is the enthalpy change when 1 mole of Al2O3 solid is produced from its elements in their standard states. Under standard conditions, they want what they are, so it's 100 kilopascals pressure and then 298 Kelvin temperature, or a stated temperature. Now it says use the table and data to calculate these questions. So look at the data first and please make sense of what's going on. So if you have to learn enthalpy changes and you're complaining about memorizing them, you are doing this whole topic wrong and you're fumbling like a lot. These enthalpy changes are important because it means it can help you decide what to do with like your Hess's law and your Born-Haber cycles. So by doing it this way, it means the way I'm about to show you will always make sure that you're always safe and always know exactly what's going on. Enthalpy change of hydration, the definition says when 1 mole of aqueous ions are made from its gaseous ions. So that means you're going to start with 1 mole gaseous ions and you're going to make 1 mole aqueous ions. Here, the enthalpy of hydration is the same. Here, the enthalpy change of solution is when 1 mole of a solid ionic compound is dissolved, blah, 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 to make aqueous ions. So then you're going to have 1 mole ionic solid going to aqueous ions. It might not have to be 1 mole, but we at least know it's going to be this. So in this, it says lattice energy of KCl, so that could be the enthalpy of lattice enthalpy of formation or lattice enthalpy of dissociation. Now, when you want to break something apart, you have to put energy in, which means the enthalpy change is positive, which means it's endothermic. If bonds are being made, energy is released, so that's exothermic. So we know that this is exothermic, so it's going to be the lattice enthalpy of formation. So that's where you get 1 mole of a solid ionic compound from its gaseous ions. The reason this is important is because it will help you decide what you're going to do in your cycle later, which is coming up right here. So it says name the 2 properties that affect the value of the enthalpy changes of hydration. So the only difference between these two is one is K+, one is Ca2+. And you can see here that this is negative, but this is like more negative. If that's more exothermic, means more bonds are made. So the only differences between these two is that one, you've got a smaller ionic radius of Ca2+, because it's got that bigger charge, and that means it's dragging those electrons in because they're in the same shell. There's no shielding between these two because they're in the same shell, they're in the same period because they're right next to each other. So the two things are what's happening is you've got an increasing nuclear charge for Ca2+, and that makes the bonds stronger when it's forming them with water and stuff. And as well as that, you've got a smaller ionic radius. Oh, it's just saying what they actually are, to be honest. You don't have to make the comparison, it's just saying those two, but there you go. And then, woohoo, here it is! So here, it says calculate the enthalpy of hydration for the chloride ions by completing this table and use labels and the data in the table. So the reason I said all of that before is because every single arrow you can see here is an enthalpy change. So you need to look at each one of them and decide what's going down here by comparing what you've been given to what is in the question. And they've told you this is the enthalpy of solution, which is where you go from a solid ionic compound to its aqueous ions. So that's that bit there. Sorry, that's that bit dealt with here. Write the numbers in as well. So this means it's going to be plus 17.2. Now we need to look at what we've got left. So that's why I've labeled all of this, because lattice enthalpy of KCl is where you're going from gaseous ions to KCl. So if I look at my table, this KCl here is a solid ionic compound. So this is this side of the equation. So the side that's not here anywhere in this cycle is gaseous ions. So in my head, I'm now thinking maybe gaseous ions is what's going at the bottom of my cycle. So if that's the case, then maybe it's gaseous ions. Let's have a look at the others. So this is the enthalpy change of hydration, which is where you're going from gaseous ions to aqueous ions. If I look at my table, I have my aqueous ions, but I have no gaseous ions. So what's on the bottom is probably going to be the gaseous ions, which is going to be K plus gas plus Cl minus gas. Now what you do is don't jump in and be like, oh, the arrows must go up because of this. You then look at them one by one and decide which way the arrows go. Do not memorize cycles. Do it this way and you'll never get them wrong. So here it is KCl. Here it is gaseous ions. So that means it's going to be, well, this is the lattice energy. This is the lattice energy, which is where you're going from gaseous ions to a solid ionic compound, meaning the arrows got to go from the gaseous ions to the solid ionic compound, so upwards like this. Then compare here and here. We're going from gaseous ions to aqueous ions, and the table has given us the enthalpy of hydration, which is gaseous to aqueous. So that means your arrows are going to be like this, going up. So then what you do is you put the numbers in. So this is the lattice enthalpy of formation energy, so that's minus 711. This is the enthalpy of hydration for potassium ions, which is minus 322. And then we don't have them for chloride, that's for calcium. So we don't know what that is, so it's going to be X. The question wants us to find the enthalpy of hydration of chloride ions, which is gaseous chloride ions to aqueous. So that is our X. Hess's law says that no matter if you start at the same, finish at the same spot, the enthalpy change will be the same. So if you start here, finish here, no matter how you get about it, the enthalpy change is the same. So then you can say that this root equals the whole other root. So the enthalpy of solution, this top arrow, 17.2 equals going this way. So we're going against the arrow, so it's going to be 711. And then from here to here, minus 322, because we're following the arrow, plus X. Then if I tidy this up, I get 17.2 equals, so 711 minus 322 gives you 389 plus X. So then X equals 17.2 minus 389, which should give you an answer of minus 371.8 kilojoules per mole. And that makes sense because it's the enthalpy of hydration. You're making bonds with water, so it's got to be exothermic, and that also adds up. So if you do it like this, you'll never, ever, ever, ever get these wrong unless you put it wrong in your calculator. Never memorize the cycle. The only way to know which way a cycle goes up or down is by deciding what goes down at the bottom, no matter what. I see people sometimes read a question where it's like, oh, it says formation, so the arrow is up. Well, you don't know that. You need to look at the table because they always do it where they add something different and people are like, oh my god, I got it wrong. So this question is about acids and bases. State what is meant by a Bronsted-Lowry base. It is a proton acceptor. And lots of people love to say proton acceptor, but don't actually know what it means. It means it will react with an H+ and it will gain an H+. So don't just blindly memorize it because you'll see it will come up and then you'll be like, oh, I don't know what to do. Oh. It says write the ionic equation for the reaction between magnesium oxide and an acid. State symbols are required. So magnesium oxide and an acid is going to be MgO solid. And we're reacting with an acid. An acid is a proton donor, meaning it's going to shove out H+. It's going to be plus H+, and then we need to think about what's happening to this magnesium oxide. So this is a solid magnesium oxide. It's going to react with an acid. It's going to dissolve into a salt like magnesium chloride and so forth. So that becomes Mg2+ aqueous. Magnesium oxide can act as a base and it's acting as an acid, so you're going to make water as well. So that O goes into water like this. It's asking for ionic equations. It doesn't want any Cl2s and all of this stuff because, I mean, it just says an acid. It's trying to get you to appreciate this H+ stuff going on here. And there's a 2H+ here to balance it out, and that should be it. Now it says, calculate the concentration of hydrogen ions in the multiplied decimeter cubed of a solution of a pH of this. So it's going to be 10 to the minus 9.43, which is just 3.7154 times 10 to the minus 10, which is roughly, follow the number of significant figures in the question, so 3.72 times 10 to the minus 10 moles per decimeter cubed. It says here, the pH of two salt solutions J and K are this, so 5 and 9. They're equimolar, so they're equal. And then it says which acids and bases could form the acid salts in J and K. So here, this is weakly acidic. So whatever we used as the acid has got to be a weak acid or a weak base. And then here, we can see it's weakly basic. So it's got to be a weak acid and a strong base. And that's pretty much it, to be honest, because it's kind of leaning more towards the 90s. So if we look at the first one, strong acid is a pH of like minus, 2, 3-ish. But we're adding a weak base, so it's not going to shoot off to like, 14 if we add extra too much by accident. It's going to get to around that 5-ish point and stay weakly acidic, so this is looking quite good. That's a strong base, so if you do it right, it'll be probably, neutral, but it could overshoot into like 14 and stuff, so that's out. Strong base, it will overshoot to like, really high numbers as well, out. And these are weak base, weak acid, it's going to be like, it's going to barely, get anywhere. It's going to be quite close to neutral, so that one's out as well. So then we're left with A, to be honest, and even if we look at the other ones, we've got HCl and H3, that would be a weakly acidic product anyway, so like this, because that's a weak base adding to a strong acid. Here, this is a weak acid and strong base, so that's going to lean more towards the higher than 7, like pHs. Okay, just for the sake of time, it says here the ionic product varies with water, blah, blah, blah. Determine it at about 45 degrees by plotting a graph. So you can plot Kw, the ionic product of water, against temperature, and then you read off the graph like this, and it gives you an answer of like, like 4.0. Just for the sake of time, I'd rather just, not like spend ages fumbling around with this. Ideally, it should be a smooth curve linking everything here as well. So now it says the ionic product of water at 30 degrees is 1.47 times 10 to the minus 14 moles per square decimeters to the minus 6. It says calculate the pH of this. Now because, so Kw, remember, is H plus OH minus. If you have pure water, then you can say that K plus is roughly H plus squared. So that means the concentration of H plus is going to be the square root of Kw, and the pH will be negative log of that. So if we do H plus the square root of Kw, that's going to be 1.47 times 10 to the minus 14. And if we do that, you get 1.212 times 10 to the minus 7. pH is negative log to the base 10 of your answer, which is going to then give you 6.916, which is also 6.92. There you go. So hydrochloric acid with concentration of this is added to this aqueous sodium carbonate, and the pH is measured. The titration curve is here. The reaction takes place in 2 steps. The reaction for the first step is this, whatevs, and then it says here, deduce a suitable indicator to identify the first equivalence point. Justify your answer using the dates in the data booklet. So just a couple pointers. Whenever you have the vertical line, that's the equivalence line, and about halfway across that, the center is the equivalence point, and that's where H plus is roughly OH minus. So then at this point, when you add either more acid or base, you get this big change in pH. Now when you're choosing an indicator, you want to choose an indicator that changes over a very narrow point, but it also needs to be around the equivalence points. It wants to be very narrow so that it's changing around here, and it needs to lie entirely across the equivalence line. The best one possible would be one that changes really narrowly, but sometimes, you got to pick this and that. So if I zoom in and let's say we've got this graph here, you want anything that kind of covers this region here, but ideally as narrow as you possibly can around that equivalence point. So we look on this diagram, we can see that our equivalence point lies at around, what's that, like, you know, 8.9-ish and stuff. So then if we look at what the best option we have really would be, is probably the 8.2 to 10, because that's where exactly, you know, that lies within it. So it's going to be phenolphthalein. And the reason is because your equivalence is around, you know, 9 or like 8.9-ish. And that's where its range lies within this. So now it says, write the equation for the reaction happening at the second equivalence point. State symbols are not required. So from this first one, it's Na2CO3, it's moving NaHCO. This NaHCO then reacts with the acid again. So NaHCO3, HCl, then, because this is another base acting as, you know, it's acting as a base and this is an acid, you can have another neutralization reaction which makes a salt plus water, but because this is a carbonate, you also make CO2. And then it says, explain how the solution at point X can act as a buffer. So this is X. A buffer in any buffer in the entire universe. Have a second to tell me what you think it is. What makes 1, 1? Okay, so any buffer in the universe is a weak acid or a weak base mixed with its salt. If you have that, you've got a buffer, you're in the clear. No matter what. A lot of people say, oh, you know, resist pH changes and this and that, blah, blah, blah. That's not useful. It's this that sets it up. So in this case, explain how the solution of this acts as a buffer solution. So at X, we have this thing met. So that means that we have a mixture of this base and its salt, which in this case is going to be, there is a mixture of the Na2CO3 and NaHCO3. The reason this becomes a buffer is because you've got a reservoir or a large amount of the A minuses, so CO3 2 minus, and your other ions here, the HCO3 minuses here. So then you need to explain how it can act as a buffer. We're adding HCl, so what it's going to do is these are going to react with the HCl. So the CO3 2 minus plus the HCl, so the H plus, sorry, gives you HCO3 minus. Because you've got this equilibrium, if I'm adding H plus, then the equilibrium will shift this way, blah, blah, blah. It reacts with this, and then this will go down. So that's how it acts as a buffer. But again, it all hinges on this, a weak acid or a base mixed with its salt. The reason you're able to tell it's these two is because we're adding HCl and we've got the CO3 2 minus ion. So there's an equilibrium happening here, and the salt is the CO3 minus here, the A minus bit. So this question is about chromium and some of its compounds. The common oxidation numbers are +2, +3, and +6. Give a reason in terms of ionization energy why chromium can show variable oxidation numbers. So oxidation means you're losing and gaining losing electrons, sorry. So if that's the case where it's able to go from +2 to +3 and +6, they must be, you know, like as you're removing electrons, the ionization energy usually climbs up. If you're able to just switch freely between 2, 3, and 6, well, not freely, but relatively easily, then it must mean that the electrons between each of these lie in, you know, similar places. So therefore, there is a gradual or small increase in ionization, successive, really, ionization energies. That's all. Or the ionization energies are similar. So then it says the bonding of the chromate ions is similar to that of sulfate ions. Draw a possible dot and cross diagram for the chromate ion. So just draw the same as the sulfate ion and then just replace it with the chromium. So normal sulfate looks like this. Here, there's your minuses, there's your double bond O, there's your double bond O. All we need to do is swap it with the chromium now. So we'll draw a circle for chromium, we'll draw this, we'll draw this, and we'll draw this, and we'll draw this. CR. Now there's a single bond between two of them, so I'm going to put the single bond here and a single bond there and a single bond here and a single bond there. And then we add the extra electrons. But this is O minus, so we need to add an extra electron to each of these. So I'm going to use a triangle as my extra electron, then just fill the rest. So 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Cool. And then these are double bonds. So there we go. 3, 4, 5, 6, 7, 8. And then while we're here, I might as well put this here as well. So that's how you do it. You just draw it out like this, and remember that each one of these is a shared pair of electrons each line. So then just transferring it to double bonds is quite easy, actually. There's an O minus here and an O minus here, so they have an extra electron, but we need to indicate there's an extra electron as well. So we could usually use another symbol like a triangle. So student added some pieces of zinc to acidified solution of potassium dichromate, and some standard electrode potentials are shown. Write the overall equation for the reduction of dichromate ions to chromium by zinc in acid conditions. State symbols are not required. So again, don't dive into it being like, oh my god, it must be oxidation reduction, this, blah, 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 blah. Based on the EMF, it tells you in the question which way to go. So it's saying reduction of dichromate into chromium 3. So this one is going in the reduction direction. And then by zinc, when you're reducing something, you have to oxidize something else. So this one's going that one's being oxidized. Now I know you could have looked here and been like, oh, that's negative, that's positive, but I always look at the main question first, just to check they've not told me which way to go already. So here you can see that this needs 6 electrons, that's 2, so you can times this by 3, and then you just combine them. So you would have Cr2O72 minus aqueous plus 14H plus, and then it's going to be 3 lots of solid zinc, so 3 Zn solid goes to 2Cr3 plus 7H2O, sorry, aqueous, 7H2O liquid, that's aqueous as well, plus 3Zn2 plus aqueous. Then it says calculate E cell for this reaction, so that E cell is E reduced minus the oxidized, so it's going to be what's reduced, which is 1.33 minus 0.76, which is plus, so that ends up being 2.09 volts. It says predict whether or not a further reduction of Cr3 plus to Cr2 plus will occur and justify your answers. So we're looking at here to here. We need to look at if anything else could do that as well. Well, you should look at the table and think, can I make this reduce with anything else on the table? Well, this is negative, so that means this could oxidize and this could reduce, right? So if that's being oxidized, going from Cr2 plus to Cr3 plus, right? But if you compare this one to this one, this is more negative, so this one would become reduced. So this would be, so if you had like a mixture, can you see how this makes this, which is then here, but you've still got zinc in the system, which can then screw up everything and then get you this. So what I'm trying to get at is, if I re-tidy this up, the first thing lets us get Cr3 plus, which is here. But then we have Cr3 plus and a mixture of zinky stuff. This is minus 0, but this one's more negative, so this becomes oxidized, that becomes reduced. So if this becomes oxidized, the Zn solid can become Zn2 plus, and then this can be reduced. Cr3 plus can become Cr2 plus. So that, it says here, the further reaction of chromium 3 into chromium 2 is possible. Well, yes, it is, because of just what I've said there. So what can happen is that Zn and H plus can reduce Cr3 plus into Cr2 plus because the E cell for the oxidation of Zn, sorry, reduction of Zn, sorry, because these are all reduced. So for the Zn solid is more negative than for Cr3 plus. So then the Zn solid becomes oxidized and the Cr3 plus is reduced. And there you go. Reduced. Whoops. All of these are showing you the EMF if you were to reduce these. So because the other one's more positive, this one shifts in the other direction, which is why we say that's negative. That's oxidized because it's shifting in the other way because that one's more positive. So it's all about equilibrium shifts, this stuff. Okay, so aqueous solutions containing chromium 3 and chromium 2 ions have different colors. Explain why these differ in color. So why? And an explanation of the origin of colors is not required. So remember that all of these are transition metals. The reason that they can do this is because electrons can move between the energy gap. So for example, here's your d orbital, 1, 2, 3, 4, 5. And then what happens is it can split into 2. So then you have this energy gap here, delta E. So the reason, so when light shines on this on the right wavelength, what it'll do is it'll absorb the light that's required for this energy gap to move into the higher state, and then the rest is reflected. And that's what gives them that color. So the difference between the energy gap here is what determines the color, the wavelength they're absorbing. And this is affected by the ligands you have, the oxidation state, and also the metal ion itself. Right here, the difference is the oxidation state. So the oxidation state is changing this energy gap. To put this in practice, imagine here's your eye, and you're looking at a green item, like a plant. White light is every single color mixed together. If you're seeing green, green light is coming back to your eye, and all the other ones have been absorbed. So this means it's absorbing everything but green, and it's reflecting green back. So in this case, these will absorb every color except the ones that are reflected back to your eye. So to put this into words now, is that they're different in color because the energy difference between the two sets of d orbitals, the two sets being these orbitals in Cr2 and 3 is different, or you could say that they have different splitting, therefore different wavelengths, or you could say frequencies of light are absorbed and reflected, and that's why you get those different colors. Every single property of transition metals, every single thing they do returns back to the fact that they form stable ions within complete d subshells. So then it says an iron nail was analyzed using this procedure. So please make sense of what you're doing. Don't just jump straight into working out moles and then trying to be like, you know, the coolest geezer ever. Like, it just doesn't work because everyone doesn't read and they don't have reading comprehension, and it's really annoying. So step by step, make a flowchart and make sense of what's going on. So they got an iron nail, they added H2SO4, they took whatever this stuff was, and they have Fe2 plus, and they made it up to 1 decimeter cubed in a volumetric flask. Then what they did is they did 25 centimeters cubed portions of this solution. So they took 25 centimeters cubed of this, and then they acidified it, whatever, and they titrated it with potassium dichromate, so K2Cr2O7, of which we know its concentration is 0.0167. Cool. So we know the concentration of this. Now they've told us the mass of the iron nail was 3.54 grams. So the very first start, we know the mass of this iron nail is 3.54 grams. The mean titer was this. So where does this tie into this whole thing? Make sure you make sense of this. The volume of the K2Cr2O7, because that's what we were using to titrate, was 15.50. The reason this is important is because it's reading comprehension, so there's lots and lots of steps you take. And also now I can see that in this thing, there's only Fe2 pluses, which react with this. The K2Cr2O7, the bits that's going to be doing all the funky stuff is this. That's just what they use to get the ions in there. You can't really have Cr2O7 2- without something carrying it. So then it says, here's a brand of nails, percentage by mass of all these nails. And it says potassium dichromate and this is a solution of oxidized iron 2 ions are shown in this equation, determined using the experimental data the brand of nails that was analyzed. So in order to do that, I need to find the percentage by mass of iron by working backwards to figure out how much iron was in what we had. So then we now exactly know what to do because we know this reacts with the Fe2 pluses, which we can see here, and then we can work back up. So then you're not working out the moles of things randomly, you actually have some flow to what you're doing and you're actually making sense of stuff. So if I do that, the moles of Cr2O7 is going to equal its concentration times its volume, which is going to be 15.5, because we've got it up there, 15.5 over 1,000, times its concentration, which was, what was that, 0.0167, which is 2.5885 times 10 to the minus 4 moles. Then I can see that this reacts in a ratio of 1 to 6, so I know that the moles of the Fe2 plus is going to equal 6 times this answer, which is going to be, and this is in 25 centimeters cubed, which is why it's important to know this flow chart. So in that case, in this 25 centimeter cube sample, we have 1.511 times 10 to the minus 3 moles of the Fe2 plus. Cool. Then we're working back up. So in the 25 centimeters cubed, we have this, but we took it from a 1 decimeter cubed sample. So we're assuming it's all evenly distributed. Fe2 plus in a 1 decimeter cubed is, remember, 1,000 centimeters cubed. So it's going to be this times 1,000 over 25, which is going to be 1,000 over 25, which is 40. So then the moles of that in the 1,000 cubed is going to be this answer times 40, which is going to be 1.5531 times 10 to the minus 3 times 40, which gives you 0.062124 moles. This is the moles of Fe2 plus in the 2 decimeter cube sample. All of that must have come from the iron nail. So that means that we can work out the mass of the Fe in the iron nail using the moles we just worked out. So 0.062124 times the MR, or the AR, sorry, of iron is 55.8, which is 3.4665 grams. Now the questions told us that it's 3.54 grams in the iron nail, and we've just worked out the mass of the Fe. So you do 3.4665 over 3.54 times 100, and let's see what we get. So 3.46 is 97.9, which is roughly 98. Therefore, it is brand D. So this question is about electropotential cells and equilibrium constants. Chlorine gas can be prepared by oxidation of chloride ions with manganate as shown in this equation in acidic solution. This H plus here tells you that it's acid solution, so sometimes they might say, there's another question, just a side point. It might be like, state what conditions this should be done in acidic, because there's an H plus there. Okay, so here we need to substitute the right values into this equation. So they've told you that lnk is the equilibrium constant that we're looking for, but it's ln, but they're asking you for k. N is the number of electrons transferred in the overall equation. E cell they've given us, and F is the Faraday constant. So lnk is going to equal, so lnk is going to be, well, they've told you that each manganate ion accepts 5 electrons, right? Now here we've got 1 manganate ion, and each one of them accepts 5. So that means it's going to be the number of electrons 5 times the E cell, which is 0.15, times F, which is Faraday constant, 96,500 per mole, over 8.31 times the temperature at 298 K. If we do that, we get lnk to equal, which gives you an lnk of 29.226. So K equals e to the 29.226. So we do that, we get 4.93 times 10 to the 12. And there you go. Now, with logs, you guys know that pH is negative log to the base 10 of your H+. To undo that, you did 10 to the minus pH. Because to undo a log, all you do is you do the base to the power of the log number. So ln k is the same as saying log to the base e. So to undo an ln, you would just do e to the power of whatever the answer, the log value was, and it will undo it. A fuel cell produces a voltage from the reaction between a fuel and an oxygen, and the reaction occurring at one electrode in a methanol fuel cell is this. What happens at the other ones? You can first of all work out what's going on. So you've got CH3OH plus H2O, and we're giving out electrons, so this is going to be oxidized. So already off the bat, we know it's got to be one of them that's reduced. So that's oxidation, it has to be one of the reduced ones. Next, we need to have a look at which one's which. So in this case, we're reacting methanol and oxygen. We're going to make water as one of them, definitely, and I don't see a water here, so it's got to be A. So the reason it's not B is because if you were to combine these, you would be saying that CH3OH plus H2O plus the hydrogen plus the oxygen gives you all of this plus an OH, and methanol does not react with hydrogen gas, so that one's out. And there you go. So lead acid batteries use the storage cells in some cars. The electrolyte is sulfuric acid, and one electrode is lead, and the other one is lead oxide, PbO2. As the cell discharges, the lead and the lead oxide are both converted to solid lead sulfate, and the concentration of sulfuric acid decreases. To deduce using the information, the two half equations happening in the lead acid battery, and then state symbols are required. So work with what the question's telling you to start with. So already they are telling you one of them is that you've got solid lead, and the other one is PbO2 solid. Cool. Is there anything else that we can tell straight away from the question that is happening? So then as the cell discharges, these both convert to this PbSO4. So both of them will have PbSO4 solid in them. So then the other thing that it must be reacted with the sulfuric acid with has to be the SO4 part. So SO4 minus aqueous, SO4 minus aqueous. Cool. But now we need to figure out the stuff to do with electrons and all that jazz. So compare your oxidation states. 0 plus 2. So it's going from 0 to plus 2, it means it's lost 2 electrons here. This SO4 minus is still SO4 minus. So there you go. That's the first one done and dusted. Second one, it's PbO2, so it's plus 2, minus 2 for each of these. Then we've got SO4 minus here, right? But if we were to then just put PbO2 and then PbSO4, we still have 2 oxygens imbalanced. So what we're going to have to do is we're going to have to add some waters to balance out our oxygen. So 2H2O on this side, liquid. But then we have to add H pluses on the other side to balance out this side of it. So then we're going to have to add 4 H pluses, aqueous. But now we need to balance the charges because we've got a plus 4 here, then a 2 minus here. So there's a plus 2 overall charge on this side, but then there's no charge on that side. So clearly we must have some electrons forming here as well, 2 minus. Then it says when solid lead sulfate is added to aqueous sodium iodide, an equilibrium is established. So this and this and all that, cool. Equilibrium constant is this. In an experiment, Kc can be determined by adding excess lead sulfate to this. So I'm going to add PbSO4 plus NaI, 25 centimeters cubed of this. That's its volume, and its concentration is 0.1. The mixture is left to reach equilibrium at room temperature. So then what they do is they add water to stop the equilibrium, and it's frozen, and then it's titrated. So they've taken this and they've added, to this mixture, they have added standard silver nitrate solution, so AgNO3. The concentration was 0.05, but its volume was 12.2 to react with the aqueous iodide from the original thing to the start. Cool. So then it says calculate the equilibrium concentrations of the sulfate ions and the iodide ions, and then hence find Kc at room temperature. Alright, so in order to find Kc, we need to find the concentration of this and the concentration of this. So we're going to have to do a bit of mole work. The question's told you at the start that they've reacted these two things, we let them reach equilibrium. So first of all, we can work out our initial moles. The overall reaction here is PbSO4 plus 2I minus goes to PbI2 solid plus SO4 minus aqueous. Now I've heard people use ice as their thing, so I'm going to switch it to ice E. So initial moles, the change in moles, the equilibrium or end moles, and then the equilibrium concentration. So don't skip out these steps. I think some people jump straight to doing concentration. Don't fumble it like that. Do it step by step. So if we look at the initial moles of the NaI, we know that this is what the scientist or chemist or whatever they did was. They got this and mixed it with this. So we can at least work out the initial moles of the I minus, which will have come from here. All right. So that means it's going to be 25 times 10 to the minus 3, or divided by 1,000, sorry, times 0.1, which means at the very start, the moles of I minus we had was 2.5 times 10 to the minus 3. Cool. Now, unfortunately, we do not know how much there was at equilibrium straight away. However, they let it reach equilibrium, they let stop the reaction mixture, and then they added AgNO3. The AgNO3, the Ag plus, is the bit that's reacting with the I minus. So whatever I minus it reacted with here must have been however much we had at equilibrium. So then we can work out the moles of I minus at equilibrium through this. The moles of the AgNO3 is going to be its concentration times its volume, which is going to be 12.2 over 1,000 times 0.05, which gives you 6.1 times 10 to the minus 4 moles. They're in a 1-to-1 ratio, so 6.1 times 10 to the minus 4 moles of this needed to react with that. So now I know at equilibrium I had 6.1 times 10 to the minus 4 moles of the I minus from the first equation. Cool. So now we can work out the change in moles from this by doing 6.1 times 10 to the minus 4 minus 2.5 times 10 to the minus 3. So we know that this fell by minus 1.89 times 10 to the minus 3 moles, the change. So then that must mean that two I minuses eventually make one of these. So it takes 2 to eventually make one of those when it reacts with this. So that means the change in moles of this has gone up by half of this, which means it's gone up by 9.45 times 10 to the minus 4. Remember that we only want the SO42 minus, so I don't really give a damn about the PBI2. We want the SO42 minus and the I minus. In this case, he only works the concentrations at equilibrium. So now I know that at equilibrium, the moles of the 2I minus is this, and now we know the change in the SO42 minus was that. We still need to find out the moles of the I minus at equilibrium as well. If you have a look at this equilibrium, remember this is them mixing it together, and then it reaches equilibrium. So if we start mixing these together and there's no equilibrium reached, the initial moles of SO42 minus is 0, and also this. So every equilibrium initially, at the very start, when you've not done any, the equilibrium's not been reached, you have 0 of each. So that means the equilibrium moles of this SO42 minus is 9.45 times 10 to the minus 3. Now we need to work out the concentrations of these at equilibrium. However, a lot of people slip up and then they add this. This isn't the concentration of equilibrium. This was just used to help find how many I minuses there were in there. At equilibrium, which is why I've written it like this, the volume was 25 when it was at this equilibrium point. They just added the water to freeze it and then carried on to try and figure out how much I minus there was in this. So you would do 6.1 times 10 to the minus 4 divided by 25 divided by 1,000. And the same for this respectively. So then your concentrations of the SO42 minus is going to be 0.0378, and then your concentration of the I minus is going to be 2.44 times 10 to the minus 2. So Kc equals the concentration of this over the other one, so it's going to be 0.0378 over, and this is squared, the I minus at 2.44 times 10 to the minus 2, all squared. If we do that, we get 63. Okay, so for in terms of its units, it's going to be moles dm minus 3 divided by mole dm minus 3 squared. So that's the same as saying mole dm minus 3 over mole squared dm minus 6, because it's squaring this, you times the indices. And also, this is technically saying moles to the 1, so then that becomes 1 minus 2, mole minus 1, and then dm minus 3 minus 6 cubed plus. And there you go. That's how you do it. Thank you very much. I hope that helps. Please like, share, and subscribe. You know the drill.